All right, my beautiful children, this video is all about planes and angles in space, which just means the angle between a line in a plane or the angle between two planes. Let's jump in. We're going to start off with a brief discussion about dimensions. Okay, zero dimensions, that's a point. A line, it has one dimension, a plane has two dimensions, a space has three dimensions. This is obvious to you, I hope. Dimensions don't stop there from a mathematical perspective. We can talk about four-dimensional, the word generally used is hyperplane, although I just prefer to call it four-dimensional space, five-dimensional space, etc. Our course stops at 3, but it's important to remember that there are things you know about one- and two-dimensional geometrical constructions because you can build up from them by analogy, and that'll help you to understand what's happening in 3 dimensions, which, despite the fact that we live in a 3-dimensional world, thinking about it mathematically is still very new and sometimes confusing to some of us. All right, we say that a vector is parallel to a plane if we remain on the plane when traveling along the vector. I would just say that the vector is on a plane or in a plane. It means the vector doesn't, stick through the plane and point out of it somehow. There's no angle between that vector and the plane, or if there was such an angle, it would be 0. Now planes are curious things. In a previous video, I encourage you to try to imagine what would the equation of a plane look like. And part of the reason that might have been a challenge at the time was because at the publication of that video, the only way to write the equation of a line that you likely knew was either y equals mx plus b or y minus y1 equals m times x minus x1, maybe ax plus by equals c. The point is some form of a line that equates two variables x and y. More recently now, we've seen that there's a vector equation of a line, parametric equations of a line, and also the Cartesian form of a line. Some of these, it turns out, will be much more natural to help us build the equation of a plane. So let's start with the vector equation of a line, right? So the vector equation of a line starts with a point, and then we add to that point a direction vector. And those are both integral parts of describing that line, because I could have that same direction vector starting anywhere in space, but that wouldn't be the same line. I need a starting point and the direction vector together. Before moving ahead to 2 dimensions, what if we bumped down a dimension and just think about a point? Well, I mean, that one's kind of obvious. That just starts with a point. And now I'm seeing that there's like a building block. There's an element that I've added here. To go from a point to a line, I still need a starting point, but I've added a single direction vector. To go from a line to a plane, we're going to do the same thing. It's going to be a point plus 2 direction vectors. And we need 2 of them because within a single plane, even if I know a point on the plane, there are still an infinite number of lines going through that point. And if I only chose one of those lines, there would be an infinite number of planes slicing through that line and going through that point. And I can't draw this for you, but I mean, I don't know. That's supposed to be like a more vertical plane kind of, I guess it would be more like that would be a better picture. Yeah. Can you visualize that though? Like even if I have a single point and a line through that point, there's still infinitely many planes passing through them. So a single point and a single direction are not enough. But if we add a second direction, then that will suffice because there's only one plane that's going to pass through, is going to contain, I should say, both of those lines and that starting point. And that right there is our first form of the equation of a plane. Check this out. Vector equation of a plane. We start with a fixed point, A, and then we have 2 different direction vectors, B and C. Each of them have their own parameter. We're using lambda and mu here, but whatever. So this, if you understand what's happening in 2D, we can apply that to 3D, and it should hopefully make enough sense. It is very important that B and C not be parallel, otherwise we wouldn't actually be able to get off of that first single line. For those of you studying further linear algebra, we would say that vectors B and C span the plane. And I'm just going to do a brief aside here, again, to explain why we're like adding all three of these together. It goes back to the point slope idea from a previous video, point slope of a line, but now we need to just extend that knowledge by analogy to space. So I start off with my point, which is wherever it is. And to that point, I'm going to add some amount of units of my first vector. And that enables me to go as far as I want in one direction and also in the opposite direction. But wherever I end up, I'm then going to add another vector. Now, if that other vector was parallel to the first one, then I would still only be able to travel along that line. However, if that other second vector is not parallel to the first one, then regardless of what direction it points in, let's say it points in that direction, I can go as far as I want in either of those directions. But if I had started closer over here, I could be going in either of those directions. Either of those. And if I filled in all of the, all of the infinite green arrows to fill in this line forever, and then if I filled in all of the infinite blue arrows going as far in both of those directions as I wanted, I would fill up the entire board, and the board is, filling in for my plane here. So and that's one way to write the equation of a plane. For lines, we had 3. We're only going to have 2 for planes. This next one looks very complicated, but actually it's rather simple, and this is the more popular way to write the equation of a plane, at least for this course. For the purpose of this explanation, please assume that x1, y1, and z1 are numbers that are known to us. So that's kind of our fixed point. We have what's called a normal vector. A normal vector is perpendicular to the plane. Just like in calculus, you had a norm was perpendicular to the tangent line of a function. Normal vector is perpendicular to the plane. Every plane is defined by a particular normal vector, right? There's only one direction you can go off of a plane that's perpendicular to it. Well, up or down. Obviously, if it's going in the opposite direction, it's just a scalar multiple. So that's not relevant. So we know that this normal, when dotted with any vector in the plane, needs to be equal to 0. So that's what we got going on here. Now that vector in the plane, vector AR, is simply going to be the coordinates of point R, which are unknown. So x, y, z, we don't know those, but we're going to subtract the numerical values from A that we do know. So if those two dotted are equal to 0, then we can write out our dot product algebraically. We can then distribute the A, B, and C, and then move a bunch of values over to the right-hand side. Those are all constants. Because I know, I don't believe I said this before, but I do know A, B, and C. A, B, and C is the normal vector for the line. And since we know what x1, y1, and z1 are, then this is a constant over here. So how to write the equation of a plane? It's just ax plus by plus cz is equal to a constant. So here's that information again. Now, I'll repeat, A, B, and C are known numbers. So like an example of the Cartesian equation of a plane might be something like, say, like 3x plus 2y minus 4z is equal to 6. And some of you might be looking at that and saying, well, hang hang on, I mean, that looks like it should be the equation of a line in 3D. I mean, it's got this, you know, we've got like an x and y for 2D, and let's just throw another variable in there. That should be the equation of a line in 3D. Some of you might even be thinking, well, you know, if I just set z equal to 0, wouldn't that be a line? So here's the real deal. What is this? What is this the equation of? If I say x is equal to 1, it depends. It depends. If the context of this is on a number line, where it's just the x-axis, then x equals 1 represents a single point. If the context of this is two-dimensional space, where I have an x and a y-axis, then x equals 1 represents a vertical line. But if the context of this is actually a three-dimensional space, then x equals 1 represents a plane. So here it is. Here's my y-axis and my x-axis. You can just about see the supposed line x equals 1 here, but again, that's only if I'm thinking about it in 2D space. In 3D space, that is actually this plane. And x equals 1 would represent a 3D space if we were considering this in a 4-dimensional geometry. I will not attempt to show that to you, but we can continue on like this. So it really depends on the context. In your youth, using x and y to describe the equations of lines was the natural choice, because that's a lot easier for, you know, like a 7th grader to wrap their head around than thinking about the vector equations of a line and talking to them about parameters and all sorts of stuff. For the purposes of our course, when we see an equation in this form, we will understand, based on the context, that it is the equation of a plane. Let's do some. Oh, before we move on, I really want to point out the important connection here from this equation to the fact that the normal vector is a, b, c, and a, b, and c are really, really crucial to forming the Cartesian equation of a plane. Knowing that makes the next few questions very easy. State the normal vector to each of these planes. The normal vector to this plane is 2, 3, -1. It's just the coefficients of x, y, and z. The coefficient to this plane, which sure looks like a line, is 3, -1, 0. This is 0, 0, 1. And this last one is 1, 0, 0. Easy. So now, given some points, can we find both the vector form and the Cartesian form of the plane? We will just do letter A. We're going to figure out two vectors in this plane. Doesn't matter which ones we work out. AB is 1, 1, -4, and AC is -1, 0, -2. So the vector equation for this plane is going to be, we'll use r is equal to my fixed point. Pick any of the points. It doesn't matter. I'll pick this one, 0, 2, 6 plus lambda times one direction vector plus mu times a second direction vector. There we go. Cartesian form. So first I need to find the normal vector. The normal vector is perpendicular to the plane. So to get something that's perpendicular to this plane, I'm going to take the cross product of the two direction vectors that I worked out earlier. That cross product is -2, 6, 1. Now, that being the normal, that tells me that my Cartesian equation starts off as -2x plus 6y plus 1z equals, over here I have a constant. And if you look back at the previous slides, they were products of these three values with our three values from our known point. In other words, this is going to be negative 2 times 0. So that was the x from here times the x from there, plus 6 times 2, those are the y values, plus 1 times 6. Add those up, we just get 18. So negative 2x plus 6y plus z is equal to 18. That's the Cartesian equation for this plane. It's not that hard to do. There's just a lot of abstract concepts that you need to be able to work through in order to get there. But once you get it, it's honestly, this is like second nature to me. There's nothing challenging about this problem. This next problem, a little bit review from previous videos. I'm not going to work through the whole thing. For part A, when it says find the parametric equations of the line through those 2 points, remember that we're going to find the vector between the 2 points, and then we're going to have one of them as a fixed point. So that'll help us have the vector equation of the line, and then from there we can go to parametric. The parametric equations in this case are x equals 1 plus t, y equals negative 2 plus 2t, and then z is equal to 4 minus 5t. Using that, hence, our favorite IB word, find where it meets the y-o-z plane. What's important to know about the y-o-z plane? What's the x value? It's got to be 0. If x is equal to 0, that means that t has to equal to negative 1. And if t is equal to negative 1, then I can find all 3 of the points. The coordinates here are going to be 0, negative 4, 9. If I want to find where it meets the plane with the equation y plus z equals 2, well, that means that y plus z equals 2. We solve this for t. Turns out t is equal to 0. Substitute that back in. That gives me 1, negative 2, 4. Notice that the y value plus the z value is equal to 2, so that checks out. And for Roman numeral 3, that we're just finding out where 2 lines intersect. That's from the last video as well, so I'm not going to get into it. If you want to try it, t should be equal to negative 6, and that will get us negative 5, negative 14, 34 as our intersection coordinate. Okay, we'll just do one of these. First things first, we got to find vector AB. Obviously, vector AB is negative 1, negative 3, negative 1. So now I want to find the equation of this plane, and I want it to be parallel to the x-axis. So that gives me the other direction vector, because the x-axis has a direction of 1, 0, 0. So I want to take the cross product of 1, 0, 0 with negative 1, negative 3, negative 1. And by the way, the order that you do this in doesn't matter. I'll show you why in a minute, but it's nothing to panic about. So anyway, that cross product is going to be 0, 1, negative 3. And then that gives me the normal vector, so my Cartesian equation for this plane will be 0x plus 1y minus 3z is equal to 0 times, okay, choose one of these. It doesn't matter because I'm still going to have 0 for the first coordinate. And then it's going to be 1 times, let's just choose point A first, because it won't make a difference. We'll get the same answer both ways. So let's do 1 times 2, and then minus 3 times, z coordinate there is 3, and that's equal to 2 minus 9, which is equal to negative 7. What would happen if I chose point B instead? Well, then I'll still have 0 for the first number, and then I'll have 1 times negative 1 minus 3 times 2. Guess what? Still equal to negative 7. So it doesn't matter which point you choose. And I said earlier that it doesn't matter what order we do that in. And that's because had I reversed the two of them, then my normal vector would have just been the opposite sign, right? This cross with 1, 0, 0. That's going to be 0, negative 1, 3. And then my Cartesian equation will be negative y plus 3z is equal to negative 1 times 2 plus 3 times 3. You can see those equations are the same, right? Like I've just moved the negative sign to the other side. So it doesn't matter which way you do it. Truthfully, I don't even have my work in front of me. I don't know. Like this might have actually been the answer to this cross product over here or vice versa. I'm not sure. It doesn't really matter because I'm getting the correct answer either way. Like I just pumped this into like a calculator online earlier and then I wrote down the answer. I don't remember what order I wrote it down in, so I just wrote down a random order here. On the real IB exam, you know, you'd want to have the right normal vector written down, even though it wouldn't make a difference at the final answer. Ideally, your grader is going to be thorough in checking your work. On my exams, am I likely to overlook that? If I'm being honest, yes. Anyhow, enough about me. Let's talk about vectors. Got to admit, this one actually had me stumped for a few minutes. It was quite an exhilarating rush for me. The first part of this is fairly easy. To find the value of k. So since we know that 1, 2, k lies on this plane, first of all, what do we know about this plane? Well, its normal vector is going to be 1, 2, negative 2. And then how was this 8 created? Right? 8 is going to be equal to the normal vector coordinates multiplied by some point on the line. So 8 must be equal to 1 times 1. Again, that's this one times this one, plus 2 times 2. Once again, that's this 2 times this 2. And then finally, minus 2 times k. That one's a little more obvious. We solve this for k. Turns out that k is equal to negative 3 over 2. Then, part B, finding the coordinates of B so that AB is normal to the plane and B is 6 units away. So, first of all, let's get a little sketch here. We've got a plane. We can let this be point A, whose coordinates are now 1, 2, negative 3 halves. And we've got B is hanging out up here. We know the distance is 6. Your first guess might be to say, oh, well, the direction vector of AB. AB is a normal to the plane, we're told. So AB should just be equal to 1, 2, negative 2, since that's the direction of the normal vector from up here. But that's not exactly true. 1, 2, 2, or excuse me, 1, 2, negative 2 is the normal vector, but we could also have a scalar multiple of that, right? I mean, we could have rewritten this equation as 2x plus 4y minus 4z is equal to 16. That's allowed as well. So 1, 2, negative 2 is unlikely to be the right answer here, and in fact, you can verify pretty quickly that that does not have the required length. So that's not going to be it. The key here is in working out the vector equation for the vector form of the equation for AB. So vector AB, we know that it starts at a given point. Right, it's 1, 2, negative 3 halves. The direction of AB is some scalar of 1, 2, negative 2, which means that the generic coordinates of point B are the x value is 1 plus lambda, the y value is 2 plus 2 lambda, and the z value is negative 3 halves minus 2 lambda. Therefore, the vector from A to B must be these coordinates minus these coordinates. So here, when I've written AB vector, that's not strictly true. That's actually the vector equation of the line passing through A and B. Down below, this will be the proper vector from A to B. So it'll be 1 plus lambda minus lambda. So that's just going to be lambda, and then 2 plus 2 lambda minus 2. So that's 2 lambda, and then negative 3 halves minus 2 lambda minus negative 3 halves. So minus 2 lambda. Okay, cool. And that's really, that was an unnecessarily complicated explanation. I mean, I could have gotten there immediately from the beginning when I said that AB had to be a scalar multiple of the normal, but I really wanted to incorporate that lambda into this so we could see where point B was. That'll be important in a moment. Anyway, I want now the magnitude of AB to be equal to 6. So it's going to be the square root of lambda squared plus 4 lambda squared plus 4 lambda squared. Set that equal to 6. We're going to solve for lambda. Lambda is going to end up being equal to plus or minus 2. And that's going to give us 2 different coordinates. When we substitute that back in for B, we might have 3, 6, negative 11 over 2. Or we might have negative 1, negative 2, 5 halves. And again, that's one point that is in one direction from the plane and another point which is in the opposite direction from the plane. All right, on to section J now. We're talking about angles. This is a formula from our textbook. It is unnecessary to memorize because you can work around this. Here we're trying to find the angle between a line or a vector and the plane. So we're interested in this angle right here, phi. We know how to calculate the angle between two vectors using the dot product rule. So the two vectors that we would use would be the direction vector of the line and the normal vector to the plane. But when we do that, we end up finding out something about theta rather than about the angle that we are interested in, phi. The book offers you, hey, instead of doing arc cosine, just do arc sine. That's fine if you want to do that. That's true. But I always just think about it as, hey, this is a right triangle here. I just figured out one of the angles. It doesn't take that much for me to figure out the other angle from there. When we do two planes intersecting, we have kind of a similar situation here. So this picture on the right, we're viewing the two planes from like beside them. So imagine, as you're prompted to here, we're literally trying to view these two planes as like a cross section. So we've got their two normals, and again, using their two normals, we can work out the angle between the normals. Then, because this is a quadrilateral here, the sum of the interior angles should be 360 degrees. And we've got two perpendiculars, which means that this fourth angle here is going to be 180 degrees minus theta, which means that the angle that we're looking for here, the angle between the two planes, must be theta, as it is supplementary to the 180 degrees minus theta that we just found. That's a long construction to go to. Guess what? The angle between two planes is the same as the angle between two vectors. You're just going to use the dot product formula. It's pretty lucky. Those two are equal. Hooray! Okay, let's do some. Let's do letter D because it looks ugly. I don't know about you, but I really can't stand reading these equations in this form. So I would have to rewrite these. So that the equation for that plane is going to be 2, negative 1, 1. That's the fixed point, plus lambda 3, negative 4, negative 1. That's my first direction vector. And then here's my second. And the equation from my line is going to similarly be 3, 2, negative 1 is my point. And then t is my parameter now, 1, negative 1, 1. Okay, I want to use the normal vector for the line and the direction vector, excuse me, the normal vector for the plane and the direction vector for the line. So the normal vector for the plane, I need to take the cross product of 3, negative 4, negative 1, and 1, 1, negative 2. When we do that, we're going to get 9, 5, 7. So now I'm going to take the dot product of 9, 5, 7 with 1, negative 1, 1. I'm going to divide that by the square root of, okay, that's 81 plus 25 plus 49. That's going to be 3. Again, for me, I'm just going to use the inverse cosine of this, which simplifies down to the inverse cosine of 11 over the square root of 465. If you just do that, that's going to get you the wrong answer. In degrees, this ends up being 59.33. We subtract that from 90 degrees to get 30.7 to 3 significant figures. And I'll just briefly comment on, I don't know, just letter E. I'm not even going to go through the whole thing because it's really the same process as the previous problem. The first plane has a normal vector that's really nice of 3, negative 4, 1. The second vector, we're going to have to figure out the normal vector, so we're going to take the cross product of those two. And then in this case, we'll just use, again, we'll do the inverse cosine of their dot product divided by the product of their magnitudes. And in this case, that will be the answer. Okay, with two planes, we don't need to subtract from 90 degrees. When it's a plane and a line, we do. All right. That's I and J. As you can see, like every time we add a new section, things are getting a little bit more abstract. Most of you watching this are probably getting a little bit more uncomfortable. Once again, one of my biggest pieces of advice here is when you get lost, try to bring yourself down a dimension and try to search for the analogies. How does what you're studying in 3D relate back to simpler things you know about 2D? And then that'll help you to get your bearings. This is a very important chapter. I can almost guarantee that there will be a long 10+ mark question on either paper 1 or paper 2 of your IB exams. It's a very popular question type for the end of the exams. So it's crucial that we get comfortable with these topics. We're almost at the end. We got like one more video for this chapter, and it's about planes intersecting in space. We're going to talk about solving systems of 3 equations with 3 variables. We'll do it on the calculator. We'll do it by hand. We're not going to do matrices unless we know that notation already. And then we're done with vectors, kind of. We actually still, I'll talk about them a little bit in chapter 16, but for the most part. Anyway, for those of you keeping tabs on my social life and mental emotional well-being, I don't bother hiding my taskbar. I think it's time for me to go home.